All right, in this unit, we are going to be focusing specifically just on dienes. And, as the name implies, we're looking at compounds that have two double bonds in them. Now, we'll probably see them have more, but, we're just kind of looking at multiple pi bonds. And we can separate dienes into a few different categories. We can look at isolated dienes. And an example of that is this, where they're kind of spread apart. And what I want to do is kind of compare them to the next one, which are conjugated dienes. And so this would be an example of a conjugated diene. You can recognize them because they have this kind of alternating system of double bond, single bond, double bond. Notice when we compare that to isolated, there is an sp3 hybridized carbon in the middle of them. So if they're separated by any sort of sp3 hybridized atom, then that's an isolated diene. You got to have for a diene this specific pattern of double bond and single bond and double bond. And in fact, any conjugated system, we can expand this out to something larger where there's multiple alternating thing system. And I'll kind of give you a better definition of conjugation in just a little bit. But the final type of diene that you can have is known as cumulated diene. And this is where the double bonds are in a row like this. Another term that you'll see for this, they're called allenes. Um, Sometimes they're drawn a little bit weird, like that middle carbon. Sometimes they'll just put a dot there. And it just means a carbon. It's just probably us chemists being lazy and trying to shorthand everything. So, but we're going to specifically focus on conjugated dienes. And the definition, technical definition of conjugation are where you have consecutive parallel p orbitals. So if we look at that conjugated system above, and I were to draw in the p orbitals, notice I have more than two, because that's just a regular pi bond, but I have these consecutive overlapping parallel p orbitals. If they're not consecutive, doesn't count, like in an isolated diene. If they're not parallel, it doesn't count. Which is going to be the case for the allenes. In an allene, this p orbital might be up and this one might be up, but this one is perpendicular. It's coming out at you. I know I can't draw it that well, but imagine that this one is coming out at you. And it's perpendicular to the other two. Now, I'll explain why it's important to have them parallel in just a minute. Now, you don't necessarily have to have a pi bond for a conjugated system to exist. So we can have an example like this. Okay. And notice here, you're like, well, wait a second. With that carbocation, that carbon there in the middle kind of disrupts things, right? Well, what's the hybridization of a carbocation? It's sp2 hybridized. And so there is an unoccupied, unhybridized parallel p orbital. So they're still all in line with each other and all overlapping. And that is the key thing with conjugation and why we care about conjugation is because those overlapping p orbitals create stability. Because if you think about it, if those p orbitals are overlapping, I'm going to try my best to kind of demonstrate this. It's going to look really messy, but imagine them all overlapping, all sharing those pi electrons in there. And anytime you can spread out electrons, we've seen this a whole bunch before, it helps stabilize the system. And so if we take a look at if we're going to go from these unhybridized atomic orbitals, we got four of them here. So four pi electrons and four p orbitals. And we're going to make four molecular orbitals out of them. And I want you to kind of look at the first two molecular orbitals here. Notice the ground state, the lowest energy. Look at all that overlapping there. All four of those carbons involved in the conjugated system are sharing those electrons. And then even in the next highest energy level, um, you have like two pairs of sharing electrons. And so molecular orbital theory here demonstrates why conjugated systems are more stable than non-conjugated systems. And if we put all four of those pi electrons in the proper orbitals, they're both in the bonding molecular orbitals, which is highly stabilizing. There aren't any in the anti-bonding molecular orbitals. So what I would do right now, before we move on, is memorize the way that these molecular orbitals look. And when I say that, know these here. Okay. And when I say know them, kind of know their order of stability, order of energies, and whether those, you got shaded, all the shaded ones are overlapping here. And then here you got a couple overlapping and then some overlapping here and so on. Because I'm going to go a lot more in depth in this later on in this unit. All right, now to round out this first video, I want to look at one single reaction. And that's what we're going to look at as conjugate addition. And, the name itself kind of says everything. We're going to add something to a conjugated system. So the foundation from this, I don't think this was chapter 6 necessarily, but from one of our previous units, the alkene chapter. All right, we did an electrophilic addition of HX across an alkene, and we followed Markovnikov's addition. Now, something interesting happens when we take a conjugated system. So this is 1,3-butadiene. And when we add HCl to this, some of the product, the H and the Cl, adds to the first two carbons of the conjugated system. And sometimes the hydrogen would add to the first one, and the chlorine would add to the fourth one. So we would call this 1,2 addition, and we would call this 1,4 addition. Now I want you to note where the other pi bond is in both cases. And here's the interesting thing. Depending on the temperature that these reactions were performed in, it would favor one of these products over the other. At low temperatures, the 1,2 addition was favored. At high temperatures, and when we say high, we generally kind of refer to anything like a room temperature and above, the 1,4 addition was favored. And what I want you to do, I'm going to stop the video here in just a minute. I want you to try to think about why this is the case. By changing the temperature conditions, one product could be favored over the other. And it's not like you'd get 100% of one or 100% of the other. It's just at low temperatures, the 1,2 addition would be the major product. You'd probably still get a little bit of 1,4. And at high temperature, the 1,4 addition was the major product. And we'll address this in the next video, but I want you to kind of, stop here and see if you can kind of come up with a possible explanation for this.